Okay, so this is problem 8.27. We are given a plane wave in air with this equation. We're told that it is incident upon the planar surface of a dielectric material with the relative permittivity of 4, occupying the half space z greater than and equal to 0, and we are asked to determine a few properties of the wave. So I've started out by drawing a picture, and we can also notice from the equation they gave us a few things, starting with we see that the amplitude of the incident wave is 20 volts per meter, and we can also see a k vector of 3x plus 4z, and we can also see that it's propagating in the y-hat direction. So in the picture, that's what I've drawn. The incident electric field is in the y-hat, coming out of the page, with the magnetic field as well, and that is reflecting off this surface of two different mediums. One of them, medium 1 is air, and medium 2 is another material with the relative permittivity of 4. So for A, we're asked to find the polarization of the incident wave. And first we see that the plane of incidence here is the xz plane, and we also see that the propagation direction for the electric wave is in the y-hat direction. So we conclude from that that it is perpendicularly polarized. And that's the answer for A. Next, we're looking for, in letter B, the angle of incidence. So the angle of incidence we can find using trigonometry. We see a triangle here. We have the k vector, and we see that this side, I'm going to draw another triangle here. This side is 4 in the z direction, this side is 3, and we're looking for this angle of incidence. So this is just you found using the tangent. So we can have the angle of the angle of incidence is the inverse tangent of the opposite over the adjacent, 3/4, and that is going to give you a value of 36.87 degrees. Now for letter C, they want us to find the time domain expressions for the reflected electric and magnetic fields. So to do this, we have a few equations to find some of the components we need. We're going to need the reflection coefficient, the transmission coefficient, and we're looking under the oblique incidence equations, and we determined in A that it is perpendicularly polarized. So we're going to need the eta1, eta2, and also the angle of transmission to find the other components that we're missing for that equation. So starting with the eta1, that's going to be the permeability of the first material over the permittivity of the first material. Since it's air, that's just going to be mu naught over epsilon naught, which is approximately 120 pi. And eta2 is mu 2 over epsilon 2, and that can be calculated with this. Since we have the mu naught and epsilon naught, we just have to multiply by the relative permittivity. So that's going to be the 120 pi by 1 over square root of 4. So that's just going to be 60 pi for eta 2. Then we are looking for the transmission angle. So to find that, we can use Snell's Law, given here. So we have the sine of the transmission angle over the sine of the incident angle is equal to the square root of. Now here we are given that it is non-magnetic material for both cases, so we can simplify this equation to simply be the relative permittivity of the first material over the relative permittivity of the second material. And we have each of these components, and now we can solve for theta t. So using algebra, that's just going to simplify to well, let's just substitute some of those values. We have theta t. We know that the incident angle is from up here 36.87 degrees, and that's the square root of relative permittivity is just 1 for the first material, and then the other material is going to be 4, and then that's going to give a value for theta t of 17.46 degrees. So we have those three components, which are going to be helpful for finding now the reflection coefficient. So this part is simply substitution. We have the eta 2 cosine of the incident angle 36.87 degrees minus eta 1 is 120 by cosine of the transmission angle of 17.46 degrees over eta 2 60 pi cosine of the incident angle 36.87 degrees minus eta 1 120 pi cosine of 17.46 degrees. And when you put that in the calculator, you should get a value of negative 0.409 for the reflection coefficient. And same thing for the transmission coefficient. We have all the values we need, so that's just going to be substitution 2 times eta 2 cosine of the incident angle divided by eta 2 cosine of the incident angle plus eta 1 cosine of the transmission angle. And that's going to give a value of 0.591. So now that we have these are going to be helpful for the next step. We can now take a look at finding the reflection, as they asked us, the time domain expression for the reflected electric field. So starting with that, we're going to have the perpendicular incident wave over the perpendicular, that's for something else. This is just going to be the reflection coefficient times the incident amplitude. cosine of omega t minus k in some k vector and then in some k hat direction. So this is just a general form of what we're looking for. Now we have the amplitude can be calculated by multiplying it. So that's going to give, we're going to use the magnitude of the reflection coefficient, and then we'll determine the direction after. So that's going to give a value of 8.18 cosine of, and then we need omega. So to find omega, we have a previous equation, which is the speed, propagation speed is equal to omega over k. In this case, we have the k vector, so we're going to need the magnitude of k. So we can find the magnitude of k by taking this value of the square root of 3 squared plus, there's no y component, and then there's just the 4 squared, and that's going to give a value of 5 for the k. And then we have, since it is an air for the first medium, we're going to have a speed, propagation speed of the speed of light. So omega is just going to be 3 times 10 to the 8th times the k, which is 5, and that gives a value of 1.5 times 10 to the 9th radians per second. So that's that value. Now for the k vector, we have that here with the 3x plus 4z, and the k hat is in the, so it's the incident wave is coming in the positive y hat direction, and we want to find where the reflected wave is going to go. So if you use the right hand rule of coming out of the page, then the magnetic component pointing this way, propagating this way, when it reflects, it's going to have the electric field pointing down and the magnetic field pointing this direction, and the propagation will be that way. So we can use that to see that it's going to be, instead of the positive y hat direction, is now going to be in the negative y hat direction. So that's what the k hat component is going to be. So we have omega 1.5 times 10 to the 9th t minus, now for the k vector, since it is reflected now, we're going to have a 3 up here and a 4 here. So it's going to be, instead of a positive 3, this is now going to be a negative 3, minus 3x, and then still a plus 4z. Because if you remember, when you do phase shifts in the cosine, it's going to be opposite the sine. And then the k hat component we said was negative y hat. And this is in volts per meter. So that is the reflection, the electric field expression. Now for the magnetic field expression, we can derive that from this. We can use the electric field reflected wave amplitude divided by eta 1, since we're in the first material, cosine of omega t minus k vector, and then the direction is going to be k hat cross e hat direction, So this amplitude we just found was the 8.18, and if you divide that by eta 120 pi, you're going to get a value of 21.7 millivolts, and then cosine of omega is 1.5 times 10 to the 9th t. Now for the k component of this, that's going to be the same k vector, 3x plus 4z, and then the k hat cross e hat is going to be, in this case, we're going to need to take a look at the triangle for this. So if we split this into its components of the x hat and the z hat components, we can look at it in a triangle form. So we have 3 here, 4 here, 5 here, the angle of reflection. We're going to have since we are taking it in components, because it takes the x hat and the z hat components and not just a single direction, we need to find out how much each component is contributing to that. So from this triangle, we're going to say that the sine is the opposite over the hypotenuse. So in the x hat direction, which is this side, it's going to be the sine of the angle of the incident angle in the x hat direction. This is the k vector. And then that's going to also add this component, the z component, is going to be the cosine of the incident angle. This would be the reflected angle, but if you remember, the incident angle is equal to the reflected angle in the z hat direction. So when you calculate that, sorry, this is going to be in the negative z hat direction, since it's that direction. And then, yeah, when you calculate that, you should get 0.6 for the x component minus 0.8 for the z component, and that is going to be crossed with now this k hat, sorry, cross e hat. You cross this with the negative y hat direction. So negative y hat cross x hat is going to give you 0.6 negative x hat. Sorry. That's that's going to be the 0.6 positive z hat direction, and then the other one is going to be minus 0.8 the x hat direction. And that's what we need for the rest of this. So negative 0.8 x hat plus 0.6 z hat, and this is in millivolts per meter for the amplitude. And that is the reflection the expression for the magnetic time-varying expression. So next is D. They're asking for the time domain expressions for the transmitted now electric and magnetic fields. So for that, we're going to start with the general form again. The transmission is going to be the transmission coefficient multiplied by the amplitude of the incident wave, cosine of omega t minus k vector with k hat direction. So now this, we have the transmission coefficient from before, that is 0.591 multiplied by the 20, the amplitude. You should get a value of 11.82 volts per meter. And then cosine, the omega is the same, 1.5 times 10 to the 9th t minus. Now for this k hat, k vector, things are going to change with the velocity now because we're in another medium. So for the k, for this equation equals omega over k, we're going to have the same omega frequency. The velocity is going to change. So that's going to be a new k value as well. So when you have solving for k, it's going to be 1.5 times 10 to the 9th over the speed of light, 3 times 10 to the 8th. And this is going to change by 1 over the square root of epsilon r2, which in this case is, we're given 4. So when you simplify this, we're going to get a value of 10 for k. And this is going to be, if this is a k vector, this is also going to have a direction, k hat. So the k hat, we need to find those components as well, the contribution of those. So similar to this, we're going to have another triangle here, and we're going to have the angle of transmission, and we have this component is going to be the cosine multiplied by the 10 amplitude, and then this side's going to be the 10 multiplied by the sine of it to get this component. So that's going to be 10 times the cosine of, we're using the transmission angle. So for the cosine, that is in the x hat direction. And then plus, going positive now in the z hat direction, sine of theta. Sorry, these are backwards. Sine is the opposite of the angle, so this is going to be 10 sine theta. This is 10 cosine theta. So that's going to change this. This is the sine theta of t in the x direction. In the x direction, and then the cosine of theta t in the z hat direction, this direction. And when you plug in the theta t, which we have, and simplify, you're going to have a value of 3 in the x hat and plus 9.54 in the z hat, and that is our k vector, which goes up here. So now we can plug that in, the 3x hat minus 9.5 for z hat. Remember to change the signs since it's a phase shift. And now the propagation direction for this. The electric field is still going to propagate in the positive y hat direction out of the page. This is volts per meter. So that is the expression for the electric transmitted field. And then the magnetic field that's transmitted is the electric, the amplitude of the transmission of the electric field, and divided by eta 2, when the second material now, in times the cosine of omega t minus the k vector k hat. So, sorry, k hat cross e hat. So we have, from this value we can calculate easily. We take the amplitude there and divide it by eta 2, and you get 62.7 millivolts per meter. Cosine of 1.5 times 10 to the 9th for omega t, and then the k hat, k vector component will be the same here. 3x hat minus 9.5 for z hat. And then for this component, this is going to have two components again, similar to this one that we have to find. So this is going to be found by the k hat cross e hat. We have the k hat from up here we solved before. K hat is sine of the theta. I'm going to give the value here. When you calculate sine of, this was the 17.46 degrees. So when you calculate that, it's going to give a 0.3 in the x hat direction, plus this cosine is going to give 0.954 in the z hat direction, and that is crossed with the positive y hat. So that's going to result in 0.3 z hat plus, minus 0.954 x hat. This will be now the component which multiplies by this, 0.9 negative 0.954 x hat plus 0.3 z hat, and this is millivolts per meter. And then for the final question they want for E, they want the average power density carried by the wave in the dielectric medium. That's going to be, we have an equation for that given by the average power density in the transmission wave is 1/2 of the real components of the electric field cross the magnetic field. We also have equations that can simplify this for us. It's equivalent to the transmission coefficient times the amplitude of the incident wave squared over 2 eta 2. And I'm going to simplify this and say that this is just the transmission amplitude squared over 2 eta 2, so that we can plug in this amplitude, which we found before, 11.82 squared over 2 times eta 2 was 60 pi, and that gives the value of 0.371 watts per meter squared, which is 371 milliwatts per meter squared. And that completes the problem.